Hello students, my name is Shashank Shekhar and we are doing a crash course on the for the upcoming JEE exam for 45 days and today is our 37th day. So yesterday we started the topic that is chapter that is organic compound containing oxygen. So we have covered the first part. So basically in that class we have covered the preparations of alcohol and phenols. So today we will sing the reactions of phenols and ether. So the remaining thing that is of that chapter that is of ether. Okay, so let us start our thing. So before that, those who are unaware about the say syllabus, you can look at this. You can have a look at this. So today we will be basically covering this part, which is ether. Okay. Then we will seeing this phenols as a whole. We have covered the acidic nature. So today we will be looking at this electrophilic substitution reaction, halogenation, nitration, Riemann-Tiemann reaction, and whatsoever. Then we will also looking at alcohol part, which includes identification of this primary, secondary, and tertiary alcohol, and the mechanism of dehydration. So this is the part that we will be covering today. Okay, so let us start our lecture. So before that, let us see the topic in more detailed manner. The first one we will sing the reaction of alcohol, which will be esterification, then the Lucas test, then reaction of phosphorus halides. Okay, then dehydration of alcohol, dehydrogenation of alcohol, oxidation of alcohol. Then on we will move to some reactions of phenol. So we will start with the electrophilic aromatic substitution. In that we will see nitration, then we will see bromination and dehydration of alcohol. So this is dehydration of phenol, you can say. Okay. Now next we will see the Williamson synthesis and reaction of alkyl halide with silver oxide. So this is of ether. So we are seeing the ether part from here. Then reaction with HX and at last electrophilic aromatic substitution of this ether, which contain benzene ring. Okay, means the oxygen is directly attached to the benzene ring. So the weightage you have seen it yesterday also. So average of one question comes, which is of 4 marks from this chapter. So let us start the reaction of the alcohol. So first we have here is esterification. So what we do, we take a alcohol, say ROH. So ROH can be anything. This R is alkyl group. Okay, so this is alkyl group that we have here. Then we react it with a carboxylic acid. Okay, so this R or R dash, they can be or cannot be equal. So both can be the case. Okay, so we'll react with this carboxylic acid and we got our ester. Now further we can use the derivative of carboxylic acid also, like this acidic anhydride or this acyl chloride, or you can say uh, carbonyl chloride. So all of the reaction are done in the presence of H plus, so acidic condition. Only this acid chloride here, which is done in the presence of a base, which is a pyridine. Okay, so these are the three reactions. So you can use carboxylic acid with alcohol, or you can use acetic anhydride with alcohol, or you can use this carbonyl chloride with alcohol. Only the difference is between this condition. So for this acyl chloride, we are using this pyridine or basic condition. Now let us see here, and you can say utilization of this reaction. So what we are taking is that we are taking a salicylic acid. So this is called salicylic acid. It is a common name for this compound, and we are doing the same esterification. So we are taking the acetic anhydride in the presence of an acid, and we do the esterification. And this ester that is formed, it is a means you can say a derivative of benzoic acid. It is a very popular medicine. You must have heard this term also, aspirin. Okay, so this is called as acetyl salicylic acid also, or you can say it aspirin. Plus, we'll have this acetic acid. So this is a utilization of this reaction, that is esterification reaction. So if you want, we can have the say mechanism also of this reaction. So what happened initially? So first this RO, okay, this attacks this carbonyl group, okay, and then this is firstly, so let me draw it for you. So we have a carboxylic acid here. So we take a strong acid that is much more stronger than this carboxylic acid. So the reaction will happen in this way. So the carboxylic acid will be less acidic as compared to this H plus, so it will be protonated. Okay. Now in the next step we have this alcohol, and alcohol oxygen has a lone pair on it. Okay. Now, due to this introduction of this H, this O is carrying a positive charge on it. Now, this positive charge make this carbonyl center much more feasible for attack of this oxygen lone pair. So, this goes here. So, first this bond pair goes on this oxygen, then it returns back, and the water leaves, and we get our ester. Now, this H2O that is left here, so it will take the H plus, and it is an acid catalyzed reaction. So you can say here that initially H3O plus were present. So I have told you earlier also that H plus is mostly present in the form of H3O plus. So H2O is released here. That same H2O is used upon taking the, or you can say, proton abstraction of this intermediate. So we are taking H3O plus as a acid, or you can say catalyst, and we are getting it back. So this is the acid catalyzed reaction. Now if you have a pyridine here, so pyridine does what? It takes the hydrogen of this ROH. Okay, so simply it takes the hydrogen of this ROH, or AR, means you can have the aryl group also in this case. So you can have this kind of group also for all of these cases. Now what happens is that this pyridine is a base. Okay, so it is a base, so it will take the H plus from here. So we will have a O minus. Then it will simply attack this nucleophilic center R dash COCl here, and we will get the, since this Cl is a good leaving group, so we will get this thing plus HCl. So this was all about the esterification reaction, and here is the most important reaction, that is using salicylic acid. So you must keep this mind utilization, so it is an important reaction. Now next we have the Lucas test. So Lucas test is also a reaction of alcohol. So this reaction is much more important, and questions are often asked from here. So it is basically a distinguishing test. So what it does is that we take an alcohol that can be primary, secondary, and tertiary, and now we have to decide that whether it is primary, secondary, or tertiary. Means we have to make the decision that whether it is primary alcohol, secondary alcohol, or tertiary alcohol. For that purpose, we use the Lucas test. And the Lucas reagent that we have here is HCl plus anhydrous ZnCl2. So we react each of these alcohols. So suppose we take three alcohols, and we have to identify that whether they are, which one is primary, which one is secondary, and which one is tertiary. So we react each of this with HCl and anhydrous ZnCl2. Now for tertiary alcohol, the reactivity is the highest. Okay, for the primary it is lowest, and for secondary it is moderate. So you can notice the time here, so several hours, so, and it is 5 to 20 minutes, and tertiary alcohol immediately gives you the product. So how you can physically identify that the reaction is completed? So something called turbidity, means some white kind of precipitation is happening. So you can see something whitish type formation. So immediate turbidity means you have formed the, you have the tertiary alcohol. So gradual turbidity means slowly means secondary alcohol. And if you are seeing the turbidity after a time, or you can say after a long time, then it is primary alcohol. So primary alcohol can also give no turbidity, means it can show no reaction also. Okay, and what is the product that is formed upon the reaction? Suppose you have ROH, and you react it with HCl plus ZnCl2, so it will give you RCl. So alkyl halide is formed in each of this reaction. Okay, so this is the Lucas test that we use for the identification of the degree of alcohol. Okay, now next we have the reaction with phosphorus aldehyde. So we have seen this reaction in the preparation of halide also, means hydrogen halides. So what we do is we take this alcohol, okay, and we react it with PCl3. So what we get? We will get 3 moles of RCl, that is halide, and H3PO3. So here we have the mechanism. So it is an SNI type. Okay, so this is an SNI type. So what happens is that this oxygen group attacks on this PCl and one of the Cl leaves because Cl is a good living group. Now, what happens? We have formed an adduct here. Okay, so adduct is formed here. Now the Cl minus attacks this R. It does not take this H. Why? Because suppose it takes this H, and then you know very well that HCl react with, sorry, H plus react with Cl to give HCl, and it is reverted back in the solution because it is a strong electrolyte. Now, since this Cl minus have no effect on this H, so it takes the R and releases the uh, positive charge on O plus. Okay. Now, further, due to this reaction, we have this kind of HPOCl2 plus RCl. So this for first mole of this alkyl chloride is released. Now we have one more H. Again, this ROH attack this pH, this intermediate, or you can say this thing, and we again get this intermediate, which is again substituted by this Cl minus R. Okay, and we get this RCl, one more mole of RCl. Now we have one more mole of this Cl that is left. So again an ROH will come and we will again get one RCl. So we take 3 moles of ROH and we get 3 moles of RCl by using 1 mole of this PCl3. Means each of this Cl is removed one by one and we get this 3 RCl plus H3PO3. Okay, so this acid is released. Now, I'm not given the mechanism of ROH. You can do it by yourself. It is a kind of similar one, but there is one short trick in it. You can say a short change in it. So if you do the mechanism, you can find it by yourself. So this is the reaction with phosphorus halide. So you can have two reagents. First one is PCl3 and PCl5. So the final product will be common for this both of this reaction. Excluding the side products, that is H3PO3, POCl3 and HCl, we will the main product, that is the alkyl halide, is the same for all of this or both of this. So that is RCl and RCl. Next we have this hydration of alcohol. So hydration means addition of water simply. You can say it in one term only, that we are adding or removing water. So that is the hydration or dehydration. So this is the thing that we have here. That is C2H5OH. So we are taking the example of ethanol. Then we react it with H2SO4 and at 443 Kelvin. So we will get an alkene here. So this is a removal of H2O from here. So how does this reaction proceed? So suppose we have this alcohol here. So in the first step, this alcohol gets protonated. Okay, so this is the protonated alcohol having positive charge on oxygen. Now, since H2O is a good living group, this H2O will live in the second step and we will get this carbocation intermediate. And in the third step, we have this elimination, means this H is released and we get back a alkene here. Now the thing to notice here is that this is the slow process. Okay, so this is the slowest process, and you know according to chemical kinetics that whichever process is slow, it decides the rate of reaction or the how fast or how slow the reaction will go. So you have studied about this rate determining step or RDS. Now, since this is the slowest process, so it will determine the rate of reaction. And in this reaction, you can see that there is the formation of carbocation. Now you can say, or you can create an analogy here, that since it is determining the rate of reaction, that means the one carbon that is forming a more stable carbon intermediate, or you can say carbocation intermediate, will be the uh, most fastest of all. Okay, so this is the thing here. This is the crisp of this reaction. Now since the carbocation stability is accordingly, that tertiary alcohol is the fastest reacting one. Then we have the secondary alcohol, and then we have the primary alcohol. So the temperature is increased accordingly, means we have to provide more temperature, because since the stability of the primary is least, we have to provide the highest temperature, it is 443 Kelvin. Then for secondary, since it is the moderate one, we have to provide 440 Kelvin, and tertiary is the least most stable one of all carbocation, So we have to provide a lower temperature, that is 358 Kelvin. Now you can see here that we have to use a strong acid for primary alcohol also, that is H2SO4. While in case of tertiary and secondary, you can do it with the help of H3PO3 or H3PO4. So this is the dehydration of alcohol. Now next, dehydrogenation of alcohol. Okay, so what is the difference between both of this reaction? So in this reaction and that reaction, basically we are doing a kind of reduction also. Sorry, you can say a reduction also, and we are using this copper here. So this is the reaction. So all of these reactions are happening at the same temperature. So whether we are taking a tertiary, whether we are taking a primary, or whether we are taking a secondary, so all of these are happening at the same rate, and the products are also different for each of this. Now, this is clear from this thing that since all of these are happening at the same rate, primary, secondary, and tertiary, there is nothing a case like, say, formation of carbocation, or you can say substitution nucleophilic, or you can say any kind of intermediate is formed. So this is a intermediate free reaction. So each of this has having a same rate and a same temperature value. Now the thing here to notice is that, so I have put up an advanced thing here. So in this reaction, what we do, it is a surface kind of reaction. Okay, so we do it on the surface of copper. So this is the copper surface that we have here, that is put upon this, or you can say supported upon this complex structure. So you do not have to worry about it. So I've just put this theory here to get the idea that okay, this reaction is not forming a carbocation, rather it is a surface reaction. Okay, now each of this will give a different product. So the first one, that is the primary alcohol, will give you aldehyde. Yep. Then the secondary alcohol that we have here will give you the ketone, and the tertiary alcohol, which cannot form this aldehyde or ketone, that will give you the alkene. So this is a very important reaction, and it takes place in the presence of copper and at high, you can say, high temperature. Now this reaction is very important in another form also, since this reaction can be used to oxidize this carbon. So basically we are oxidizing this carbon here because we are removing the hydrogen. Yeah, so we are oxidizing this carbon, and we can form a ketone from alcohol. That is, we can oxidize this alcohol and form ketone in aldehyde accordingly. So for first degree, we have this aldehyde, and for 2 degree, we have this ketone, and for 3 degree, we have this alkene. Now next, we have oxidation of alcohol in a more fascinating way. So I put up just a table, and using this table, you can easily determine that which will give which reaction. Okay, so children often get confused that which reaction or which should be used. Okay, so this is the thing that we are having here. So we are having three type of alcohol, and we are taking different reagents. So if it is an primary alcohol, and if we are using KMnO4 or K2Cr2O7 or CrO3, so if any of these is present here, then aldehyde is first converted into aldehyde, and on further oxidation, or you can take say on taking further equivalence, you can convert into carboxylic acid. In the secondary alcohol, it directly converts into ketone. You know very well that it converts into ketone, and now secondary ketone cannot be converted into carboxylic acid very well. Okay, so this is the thing. So the same reagents are used, but for the tertiary alcohol, the case is different. Since tertiary, if you want to convert this tertiary alcohol in this carboxylic acid, so it, or you can say aldehyde or ketone or anything, you have to break one CC bond. So one CC bond has to be broken so that you get your final product. Now to do this, we take the strong reducing oxidizing agent, that is KMnO4 of course, and we plus have an elevated temperature. So we do have to have a elevated temperature so that this cleavage of CC bond takes place and the formation of carboxylic acid takes place. Okay, so this is all about the oxidation of primary, secondary, and tertiary alcohol. Now let us move on to a, you can say, a weak reducing oxidizing agent as compared to CrO3 or KMnO4 or any of this, that is PCC. So what is the use of PCC? So this PCC is important because if you are reacting alcohol or an allylic alcohol or an allyl alcohol with this PCC, it will form aldehyde only. So it is a weak reducing agent, weak, sorry, oxidizing agent, weak oxidizing agent. Okay. So since it is a weak oxidizing agent, it will only convert this alcohol into aldehyde, and it will not do its further oxidation into carboxylic acid. So this carboxylic acid will not be formed. So this is the very important use of PCC, that it converts only up to aldehyde and does not convert further into carboxylic acid. So this is used. You can use this PCC here also, no problem. Okay, so this is used for the conversion of alcohol into ketone also, secondary alcohol, but it cannot be used here since it is a mild oxidizing agent. So you can add PCC here, but the thing that is to be noticed, it converts into aldehyde only. So this was all about the oxidation of alcohol. Now let us move to nitration of phenol. So now we will see the reactions of phenol. So basically we will see the electrophilic aromatic substitution of this phenol. So first we have this nitration. So two cases can arise. So if you take dilute HNO3, okay, so if you are taking the dilute HNO3, then a simple orthopara product will be formed. So you know very well. So if you have seen the structure of this phenol, then you can clearly see that this has a lone pair on it, and I have told you earlier also. So it is an electron donating group through the plus M effect. Okay, so it is an electron donating group, and it shows plus M effect, or you can say plus R effect. And one more point is that it activates the ring. Activates the ring. So these are some important points about this phenol. Okay, and we also know that if something has to be electron withdrawing, then it should have a structure like this or like this. So here is the phenyl group that should be present. But since it is having this kind of structure, that this has a lone pair, okay, so it will donate it electron. So this will donate this electron here. Now this lone pair of electron will move across this ring, creating negative charge on ortho and para position. So this is the resonance structure that we have. So this is the ortho position, and this is the para position. On further movement of this lone pair, it will move back to this thing here. Here it will move at last. So we have three positions that are here, here, and here, out of which two is ortho and one is para. So accordingly, we will be getting our products. Now let us see the reactants. Oh, sorry, the products. So for dilute HNO3, we will get our normal products, that is ortho and para, in which para will be present in good amount. Now coming to this conc HNO3. So if we take this conc HNO3, then what is the difference? So it will give a tri-substituted phenol, which is called as picric acid. So those who have not attended previous class, so we have another example also. So if we take, so we can form this picric acid in another way also. So if we take this Cl, okay, and try substituted NO2, then if we just pour warm water, H2O, that is warm, then we will get this thing. So this will follow a nucleophilic substitution reaction, because this NO2 deactivates this ring and it becomes feasible for the substitution of this Cl. And we can also get this picric acid in this way also. Or we can pour this conc HNO3 on phenol. Okay. Now let us see you can see a very important concept here, that is of ortho and para nitrophenol. So you know very well about this hydrogen bonding. So if a hydrogen is attached to chlorine, okay, oxygen, fluorine, or nitrogen. Sorry, chlorine is not the one, or nitrogen. So if hydrogen is attached to any of this, and further it is in close proximity with any electronegative element, say X, then it will form a kind of hydrogen bonding here. So two things are to be important. First, that it should be attached to any of this oxygen, fluorine, or nitrogen, and second, it should be closer to a electronegative thing like oxygen, fluorine, nitrogen, chlorine, or you can say any of these three also. Yeah. So in that case, hydrogen bonding will be formed between this electronegative thing and this hydrogen. So keeping that in mind, so if we have this orthonitrophenol, we can have a hydrogen bonding. So this is the nitro group, and this is the alcohol group that is present as ortho position. Now this H can form hydrogen bonding with this alcohol, or sorry, nitro group. Similarly, if we have the para, we can also have a hydrogen bonding like this between two different molecules. Now, if you see the difference between both of this, you can see one thing, that the first is forming a intramolecular hydrogen bonding, meaning that hydrogen bonding is formed between two atoms that are of the same molecule. That within the same molecule we are getting the hydrogen bonding. If you compare it with the hydrogen bonding of this paranitrophenol, then we have two molecules. The first one is this one, and the second one is this one. And the hydrogen bonding is between these two molecules. So it is called as intermolecular. So first one is intramolecular, and the second one is intermolecular. So intramolecular means within the same molecule, and intermolecular means between two different molecules. Now what are the effects of this, say, hydrogen bonding? So the first effect is on acidity. So what happens is that the acidity of orthonitrophenol is greater than paranitrophenol. Okay, so why is it so? So the reason behind it is that intermolecular hydrogen bonding is much more stronger than intramolecular. So if you consider the strength here, then intermolecular hydrogen bonding is stronger than intramolecular hydrogen bonding. Now due to this reason, this H that is present here is easily released as compared to this H, which is in intermolecular hydrogen bonding, this H. And you know very well what is acidity. So it is basically, according to this RNS concept, it is the giving of this H plus. Now since this H is, say, combining, or you can say interacting with this phenol group or nitro group with intramolecular, which is weaker as compared to this one, so this H will be released easily. So orthonitrophenol will have a say higher acidity. Now the second effect is that the boiling point of this paranitrophenol is greater than the orthonitrophenol. Why is it so? Because to boil something we have to form its vapor, and we have to make it volatile. And how it will happen? So you have to break this bond in both cases. Sorry, in this case only. And you know very well that this hydrogen bonding is stronger in case of intermolecular. So this will break easily for this intramolecular as compared to intermolecular. So intramolecular has only van der Waal only van der Waal case of van der Waal type of interaction. It can have a intermolecular, but since this hydrogen is distributed between both the in this molecule and other molecule, it is not that efficient intermolecular. So this one is more efficient, so it will require more energy, and hence the boiling point of paranitrophenol will be higher. Now next, let us move to bromination. So bromination can have two type of reaction. The first one is with Br2 in presence of CS2. So this CS2 is nothing but a solvent that is used here. Okay. So it is used in the presence of CS2, which makes it less reactive as compared to this Br2, because CS2 is not that much polar. So this is the reason we are using this CS2 here. Okay. Now since we are using a less polar reaction, and this electrophilic aromatic substitution is a kind of involving a formation of intermediate which is positively charged, and you know that this kind of intermediate is much more stabilized in polar solvent. That is why we use a non-polar solvent, that the rate of the reaction is, you can say, diminished as compared to the polar solvent. So this give us a normal product, that is first upon ortho and second upon para, in which para is the having the higher, you can say, yield. Okay. Now if we take simple bromine water, that is Br2, then it will react in a rigorous way, and it will be tri substituted at both ortho and one of the para, sorry, one para, and it will give 2,4,6 tribromophenol. So this is the main difference between CS2 in Br2 and bromine water. Now you know a thing very well, that it can be asked in such a way that tell which of this will discourage the bromine water. So if phenol is written, then it will of course discourage the bromine water. Now coming to other electrophilic aromatic substitution like chlorination, Friedel-Crafts reaction and sulfonation. So they are done in a similar simple way like this. So it will simply give ortho and para substituted phenol. So this was all about the electrophilic aromatic substitution of phenol. Now let us move to some other reaction of alcohol. So here we are doing a dehydration of alcohol to give the ether. Okay. So this is a different kind of reaction. Okay, so the difference is that we are taking conc H2SO4. Okay, and we are taking 2 moles of alcohol. So how does the reaction proceed? So it basically is used in the preparation of ether. So you have now moved to ether. So those who are not aware about the structure of ether, it is like this. One is R, one is R dash. So this R can be equals to R dash or not equals to R dash. So in both cases, it is called as ether. Ether have oxygen that is having a lone pair, which will affect the reactivity of this ether as well. So first of all, we will see the preparation of ether. So what we will take is that we will simply take an alcohol, and we will take H2SO4 and 140 degrees Celsius. It will give an ether which is a symmetrical ether, because we are using only one kind of alcohol. Now if we use two type of alcohol, so like this and this, then it will give an unsymmetrical ether, or you can say three unsymmetrical ether. So one with the same molecule, so suppose it is, so it will be 2 here, sorry, but you can say that 3 here, 3 of this and 3 of this, sorry, yeah. So one CH3 can form one symmetrical ether, that is CH3OCH3, that is here. Then CH3CH2OH can form another symmetrical ether, that is CH3CH2O CH3CH2. Okay, and the third one is the hybrid of both of this, that is CH3O CH3CH2, that is this one. So this is the dehydration of alcohol. Now how it will happen? So first of all, it will start with the protonation of this alcohol, that is this one. Okay, now in the next step, what will happen? Another alcohol molecule will attack here, and it will give us this kind of intermediate. At last there is a deprotonation of this oxygen, and we get back our ether. So this was the dehydration of alcohol to prepare ether. Now second is the most important method, that is Williamson synthesis. Okay, so what we do in Williamson synthesis? So we take an alcohol here and we react it with metal. Now you have those who have seen it earlier, so you must have known that on reaction of alcohol with a metal, we get an alkoxide. Yes. Now in the next step, this alkoxide will attack an alkyl halide here. So what we are taking? We are taking an alcohol here, and then we are reacting it with aldehyde in the presence of metal. Okay, and this O minus, which will act as a nucleophile, so this will act as a nucleophile now. So it will attack here, this CH3CH2, and this Cl will leave, so as to get our ether plus NaCl. So this is overall Williamson synthesis. So it is a very important reaction. Now the exception that is to be kept in mind is that it cannot be used with an halide that is tertiary in nature. Why? Because the reason is very simple. So of in place of giving the nucleophilic substitution, it gives the elimination. So here elimination take place. Why? Because since there is a kind of steric hindrance that is present here, so the alkoxide that is formed, it is not very suitable for attacking here. So in place of say attacking and removing Br, it simply takes an H plus, or you can say proton abstraction, and do the elimination reaction to give our alkene. Now which alkene will be formed? So it will give a thermodynamically stable product, that is a more substituted alkene will be formed here. So this is a very important point. It should be kept in mind that first of all, if we take a 3-degree bromine and we do the Williamson thesis, we will not get our ether product. So it is not a Williamson thesis at all. It will simply give you then alkene, and not only alkene, it will give you a substituted alkene. Plus we will get an NaBr and an alcohol. So this is the Williamson thesis in all. Now let us move to another reaction, that is reaction of alkyl halide with dry silver oxide. So it is also a preparation method that is used for the preparation of ether. So we take alkyl halide in the presence of silver oxide and we will get our ether. So this is an additional reaction I have added. So it can be used in places if you have to do the synthesis or if you are asked in exam. And you will get a silver bromide which is precipitated. So you can use this reaction very well because the side product is precipitated and can be filtered easily. Now I have put up a slide of reaction with HX here. Why? Because HX was an important one, so I thought it to keep it more in a detailed way. Okay, so this is a reaction with yeast ether. So what we are taking? We are taking an ether and we are reacting it with HX. Okay, so we will see this thing. Okay, so when we will solve question also, you will get in close with something. So this reaction order is like this: HCl, then HBr, then HI. Okay, now what we do, will get in this reaction. So we'll get an alcohol plus R dash. Okay, so these two products will be formed here. Now in this reaction, the R dash X will be 1. Okay, so in this reaction, it happens in this way. The R dash X will be 1, which will having the less hindered one. So in both of this R and R dash, the X will be attached to that alkyl group which is less hindered. So X is attached to less hindered alkyl of either of this. So this is all over reaction with HX. Now let us see some of the electrophilic aromatic substitution of ether, which is having a phenyl group. So what we are taking? We are taking 3 of the reactions. We are simply taking anisole. So if we do the bromination, we will get para and ortho, in which para will be major. So I will not put much pressure on this. So you have seen this reaction earlier also. So I am just saying that yes, these are also possible with ether. Now second we have this anhydrous CS AlCl3 in CS2 in the presence of CH3Cl. Again we are using a CS2, a polar solvent, so as to you can say minimize the reactivity. Now again we will get the Friedel-Crafts reaction, that is Friedel-Crafts alkylation and Friedel-Crafts acylation. Again the para will be in the major form. At last we have this nitration. We take this nitrating mixture and you will get this para and this ortho, and para will be in the major form. So this was all about ether. So we have today covered the reactions of phenols and alcohol. Then we have seen ether, what is ether, and their preparation and their reactions. Now we'll see some questions one by one. So among the following alcohol, which would react fast with conc HCl and ZnCl2? So ZnCl2 and HCl2. So this is nothing but our Lucas test. So for those who don't know, that Lucas test is, I've told you in the first slide also, sorry. So third degree is reacting faster, then second degree, then our first degree. So which one of these is the third degree? So this is pentanol. That means CH3, CH2, 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 OH, CH2OH. So it is a 1 degree. Similarly, 2-methyl butanol. So we have a 2-methyl butanol. 1, 2, 3, 4. So this is present at 1. So it is also a 1 degree. Then we have 2 pentanol. So 1, 2, 3, 4, 5, 2 pentanol. So it is a 2 degree, and 2 methyl 2 butanol, which means this one. So this is a third degree. So it will give you the fastest reaction. So the same thing is written here, that the Lucas test react with it 3 degree faster. So this will give our fastest reaction, which is a third degree alcohol. Now next, an unknown alcohol is treated with Lucas reagent to determine. So this all are the questions from JEE only, or you can say related question from JEE only. Whether the primary, whether this alcohol is primary, secondary, or tertiary, which alcohol reacts faster and by what mechanism? So you know very well that tertiary will react faster. Now tertiary, so if you know that tertiary, okay, tertiary will react faster, then it is most probable that it will go through SN1, because SN1 involves the formation of carbocation, and carbocation forming is being formed stable for this tertiary alcohol. So this is the answer, that is B. Now next, we have this rate of dehydration follows the order. So we have this dehydration. So what was dehydration? So we are taking an OH here and a H here, and first we were protonating this one, and it was leaving like this. So we can see very clearly that it is having again a formation of carbocation. So third degree will form faster, then second degree, then first degree, and then this methyl alcohol. So the same thing is written here also. This is the answer. Next, the major product obtained on interaction of phenol with sodium hydroxide and carbon dioxide. So what we are taking? We are taking a phenol and a sodium hydroxide. Then we are taking carbon dioxide. So this is Kolbe electrolysis. So I have not taught you Kolbe electrolysis because I know that question will be enough to solve this. Okay. So how it will proceed? So NaOH will act as a base first of all. It will act as a base and form kind of this reaction. Okay. So it will take this proton from here. Now in the second step, what will happen is that since we are having a O minus here and a Na plus with here, okay, so NaOH will react and give us H2O. So let me do it on a board. So this is Kolbe electrolysis. This is an important reaction. In the first step, this NaOH will react in the presence of CO2 to form this O minus Na plus, okay, plus H2O and this CO2. Now since it is having a positive charge here, so it will kind of form a let's say it will have an interaction between a ion and a dipole. So this is a very good example of this interaction one. So since it is a dipole, because not it is not having a dipole moment, of course, because this is a symmetrical molecule, but it will all form this delta negative charge here, a delta positive here and delta negative here, because oxygen is more electronegative, and since it is a sodium ion that is positively charged, so it will interact with this OX using electrostatic force of interaction. Now next what will happen? So this will come in close proximity. Now due to this lone pair will move here and this will attack here. So you will get this kind of thing. Okay. O minus, Na plus, and then CO O minus, having a positive charge. Okay, so this is the overall that we will have. So it will move further away. So we have this Na plus. Okay, and we are having a hydrogen also here. Now this Na plus, since it is a base, it will take this H. Okay, and this will be protonated first of all. So this will be protonated by this H2O, and we will get here OH. Now at last, since Na plus is present here, it will take this proton from here, and we will get this OH, H, and C double OH. So this is the final product that we have here. So if you look at the option, we have benzoic acid, so it is not the answer. Salicylaldehyde, no. Salicylic acid. So salicylic acid is like this. So those who do not know, this is the structure of salicylic acid. So the same thing is written here also. Okay. So at last we do the protonation to give our final product, salicylic acid. Now this is the last question that I will solving. Then you will solve list of the question by yourself. I'll just show you the questions. So sodium phenoxide react with CO2 at 400 Kelvin and 4.7 pressure to give. So what is sodium phenoxide? It will look like this. So you will do it by yourself. So it is a known question. So I solved tutorial also. So let us solve this question, that is phenol on treatment with CHCl3 and NOH gives salicylaldehyde. The reaction is called, so this is an example of Reamer-Timmer reaction. So what happens is that we take OH, react it with CHCl3 and NaOH. I will not show you the mechanism here. Why? Because it involves carbene, and carbene is not included in your syllabus. So we will not seeing at the mechanism. So it is a kind of salicylaldehyde that will look like this. So it is similar to salicylic acid, only we are removing this carboxylic acid by aldehyde, and so we call it salicylaldehyde. So this is the salicylaldehyde. So this is a Reamer-Timmer reaction. So this two reaction, that is Kolbe reaction and this Reamer-Timmer, are very important. So you should have a look at this also. Now rest of the question I will just one by one show it to you, and you will solve you by yourself. So I have not solved any question of ether because it is not that tough to solve. Okay, so I've just put up a reaction, this example here, so you can do it by yourself. So this was for today's class. So I've covered this alcohol, phenol, and ether of this oxygen-containing carbon compounds. Now next, in the next class, we will see aldehyde and ketone and carboxylic acid. Okay. So thank you for your time. If you have any questions, you can ask now.